Ladies and gentlemen, soap bubbles and mathematics. Soap bubbles are actually a serious topic in mathematics and one with lots of applications. I go to big international conferences and I hear scientists and engineers talking about how to design foams to put out fires or to force oil from underground or to model biological cells. Here I'll show you some human cells that look and act a lot like soap bubble clusters. So here I'm going to show you now some human cells that look and act a lot like soap bubble clusters. There are scientists at Trinity College, Dublin, that study solid foams of cellular materials, like the bee's honeycomb, light and strong, and therefore very good for designing lighter parts of lighter cars and airplanes, strong, comfortable running shoes. Of course, they want to make nice mattresses for us. I have a pillow that's something like that one there. Meet bakers wanting to have exactly the right size bubbles or holes in the crumb. Coffee artisans that are trying to design the perfect foam for the cappuccino. The Beijing Swimming Olympics pool, where Michael Phelps set all those records, was built on a soap bubble model. But when you have clusters of millions of bubbles like this, they can get quite complicated. And so, mathematicians like to start with the simplest example, which ought to be a single soap bubble. Now, a soap bubble has some nice features. There are some nice ones. Some more. There's a double bubble. Oh, there's a nice big one there. They have a very distinguishing feature, their shape. These bubbles are round. That's what we notice. Why are bubbles round like that? Well, the reason is a geometry reason, a mathematics reason. It was in 200 BC that Zenodorus proved that a round circle is the least perimeter, most efficient way to enclose a given area in the plane. And then it was 2,000 years later until Schwartz proved in three-dimensional space that the round sphere is the least area way, most efficient way to enclose a given volume of air. And similarly, when you have a cluster of soap bubbles, they're looking for the least perimeter, most efficient way to enclose and separate several regions of prescribed volume. But now the math gets much harder, because the simplicity and smoothness of the bubble disappears where the pieces of bubbles come together at those singular places. And so to study those kinds of bubble clusters in any depth required waiting for the advent of a very technical so-called geometric measure theory. Some of the pioneers were L.C. Young at Wisconsin, De Giorgi in Italy, who was mentioned earlier today, Reifenberg in England, and that famous duo of Herbert Federer and Wendell Fleming at Brown. I visited Federer and his wife about 10 years ago at their retirement home in just outside of Providence. That was about 5 years before Federer's passing. But Fleming is still going strong, and he was a student of L.C. Young's. And I asked him what it was like back in those early days, what L.C. Young was trying to accomplish with these more general definitions of surface that allow all kinds of singularities in topology. And this is what Fleming had to say to me.
Goal was to develop a very flexible theory which would enable one to do geometric problems in the calculus of variations without prescribing the topological type of the surfaces that one's dealing with. Also to do this in an arbitrary number of dimensions. Since inevitably there will be singularities, one has to allow for surfaces with singularities. And so his theory of generalized surfaces, which later morphed into Fred Ongen's theory of varifolds, really was a framework in which this succeeded.
So he mentioned there the notoriously technical theory of Allard and Almgren with varifolds, which eventually led to Gene Taylor's complete classification of what soap bubble clusters look like and what the singularities look like. Here's one of my favorite old pictures that was taken back in 1965 on the steps of the Scuola Normale Superiore in Pisa, where you see Fleming, Almgren, who was my thesis advisor, and De Giorgi. Unfortunately, so De Giorgi died in 1996, and then Almgren about almost exactly 100 days later. But the work goes on, and there's still basic results being proved. I just saw on the internet last Thursday a new announcement by Neighbor and Valtora about what in high dimensions the singular sets can look like, how they're stratified, even though it's still an open possibility that the strat in the various dimensions can have lower dimensional, fractional dimensional pieces. The original theory was all in Euclidean space, but then it followed from Nash's embedding theorem, which we've heard so much about, that you can take curvy spaces and put them in Euclidean space and then apply the theory. So at least one of the Abel Prize winners had an important part of the soap bubble theory, not to mention, as we heard earlier today, about the De Giorgi-Nash theory. But enough talking about mathematics. Now we're going to do something here, and in fact, when we do it, you'll all be a part of it. We're going to have a little guessing contest. Don't need to know anything for this. Just see how much you'd like working in soap bubble mathematics. So here's the first question. And this has to do, I have a bucket of soapy water over here. And if I dip a wire in the soapy water, nice film. This is just a homemade wire I made, you can tell. Nice film forms across it. And now if I take another soap film, can that first one go straight through the other one? So there's the question. You can all vote. How many people vote yes? One can go straight through the other. How many people vote no? Will not go straight through the other? Well, the answer, it's almost yes. It doesn't have to break. Now we're getting some breaking here. It's a little embarrassed, the soap film. But here you can see it. It's going through, but not straight through. There's a peculiar deflection or hole as it passes through. It's kind of a strange thing. You're welcome to come down and get a closer look later, but I'll just show you some pictures now that the answer is almost yes, but at the last minute, there's some kind of strange red deflection or hole at the center. Sometimes a very clear hole that you might see with certain models. Well, now, if you didn't get that question right, don't worry. The goal here is to get at least one question right today. And we'll go right on to question number 2, a kind of one that's related to high school geometry, Fermat's problem, which is to find the shortest road system connecting the 3 vertices of a triangle. So we want to use the least amount of concrete, and the question is where to put the central junction. Well, you learn in high school that the angle bisectors meet at a point. Maybe that's the best one. Or B, the perpendicular bisectors' sides meet at a point. Maybe that's the best one. Or maybe the angles at the center should all be the same. So how many people are going to go with A, angle bisectors? Nobody with that? Oh, good, thank you. One courageous soul in the back. How many people go with perpendicular bisectors' sides? Okay, we've got a couple more votes for that. 1, 2, 3, 4. How many people go with equal angles at the center? Oh, this looks like the landslide choice. Not always right in math, but right in this case. That's right, they meet at equal angles. And this is something you can illustrate and learn from soap films if you have them between plexiglass plates, joining cities. They keep wanting to minimize length, and they keep moving until they're perfectly happy and balanced at equal 120-degree angles. Because if 2 of them were pulling in the same direction, the junction would move that way to make 2 of the roads shorter and just 1 of them longer. And ladies and gentlemen, we're going to try that here today, if permissions permit, because I brought along some plexiglass plates. We can take that picture off. I'm going to do that. Oh, or you can do that. Good. Or I'll do it. There we go. Oh, no, we don't want that on. Back to my picture. Back to me. That's it. Black. Good. Back to me. So we'll dip this in the soapy water, and now you'll be able to see here. You said, I don't know, it went rather quickly, moved into that balance of the 3 equal angles. Now, it didn't see this road over here. Oh, there we go. Again, sliding until that perfect balance. We have 2 junctions where the angles are meeting in 3s at 120. go. Now we're getting the complete picture. See, it keeps moving until they're perfectly balanced with those equal 120-degree angles. There it is. That's actually the shortest road system joining the 5 vertices of the regular pentagon right there. So the soap bubbles found it, that perfect length minimizing, area minimizing configuration with those 120-degree angles. And actually, in soap bubble clusters, like this double bubble here, wait, there we go, like this double bubble here, the big bubble, the little bubble, and the separating surface all come together at 120-degree angles for the same reasons of minimizing length or area or energy. This was observed by the Belgian physicist Plateau back in the mid-1800s, and it took 100 years until there was a mathematical proof that that's what ought to happen in geometric measure theory by Gene Taylor in 1976. Okay, folks, here comes your hardest question now. How many different ways can pieces of soap films come together? So we saw one way already, right? You can have 3 meet at 120-degree angles. We saw something that can't happen. You can't have one soap film cross straight through another soap film. That would be 4 meeting at 90-degree angles. So here are your choices. A lot of choices to guess. How many of you guess A, there's just that one way? 1, good answer in math. How many people say no, 2, maybe there's another way? 3, a few. 4, a number. E, a larger number. F, over 100, but finite. G, infinitely. There's the landslide vote again, infinitely. Now, of course, in math, the answer to these questions is always either 1 or infinity. And in this case, the answer is, the answer is 2. What? 2? 2 ways. 2 ways, a very strange kind of thing. There's the way we've seen already, where you can have 3 pieces of surface meeting along a curve at 120-degree angles. And then there's a second possibility, which occurs in the triple bubble there, where 4 such curves and 6 pieces of surface come together, the curves meeting at angles of about 109 degrees. This was exactly what was proved by Gene Taylor in 1976. And there's a footnote I've got to mention on part 1, because she proved that the curves were somewhat smooth, but the ultimate smoothness, the real analyticity of the curves, was proved by our other Abelist, Nirenberg, with collaborators, a couple years later. So I guess both of the Abel Prize winners contributed significantly to soap bubble theory. Makes me especially proud to talk about it today. So here was this result of Gene Taylor's, and this interesting singularity in red there, especially the one at the bottom where you see the 4 curves. Let's take a closer look at that. So if you look at that under a microscope, the 4 curves would look like straight lines, like the lines going from the center of the tetrahedron out to the 4 vertices at angles of about 109 degrees. And the 6 surfaces, that is the 3 bubbles and the 3 separating surfaces, would look like those flat triangles going out to the 6 edges of the tetrahedron, the 3 coming down from the top and the 3 around the bottom. Now, so theoretically, if you dip a tetrahedron in soapy water, you ought to get something like that. What actually happens, well, sometimes it breaks. Sometimes you get a bubble. But otherwise, you'll get exactly that kind of singularity where the 4 curves coming in from the 4 vertices and the 6 pieces of surface coming in from the 6 edges all come together at the center of the tetrahedron. So there is that second kind of singularity. The second kind of singularity. Of course, the astonishing thing about Taylor's theorem is that those 2 singularities are the only 2 you ever see, no matter how complicated the soap bubble clusters get. Next question for you. What will happen when I dip this cube in soapy water? What will happen when I dip this cube in soapy water? So there will be 4 choices here for you to vote on. So how many people think everything will come together at a point? How many people think everything will meet in a line? How many people think everything will meet in a little square? Really? Okay, that's the majority here. Let's see what happens. It's the little square. There it is. How does it know to do that? There it is, the little square. Pop. As long as it lasts, it loves that little square shape. Now, of course, there is a way you could have figured that out using this principle that the curves always meet in fours. If everything met at a point from the 8 corners, they'd be meeting in eighths. Or if you had a line in the middle, the end of the line going out to 4 of the corners would be a total of 5. But if you have the little square in the center, at each corner of that little square, you have 2 sides of the square and 2 lines radiating out to vertices of the cube for a total of 4. Okay, good. Now keep track of the number you get right here. Next question is for this long triangular prism. So again, there are 3 choices here: point, 2 points, or triangle. But I want to help you a little. Remember the principle. Curves always meet in fours. So the first one looks like it's not fours. It looks like all 6 are meeting at the center. But the other 2 look like 4, right? In the long, if you have a line, at the end of the line, you also have 3 vertices of the triangular prism. Or if you have a little triangle, you have 2 sides of the triangle and 2 vertices of the triangular prism. Okay, so what's your vote? How many people are going to go with A anyway? Yeah, no, really? Oh. How about B, the line? Okay, how many people go with C, the triangle? Oh, it's about tie here. It's about tie here. Okay, we're going to see what happens. Dip it in the soapy water. Broke the first time. Oh, it's getting a little, we have a little too many bubbles in here. Got to clean that out a little. Yeah, like the lab sciences, we got a little of that here today. There it is. There's a line. There's a line in the center there. There's a line in the center. So that's the right answer. That's how you get credit. Now, the triangle is sort of possible if we didn't have such a long triangular prism. I said a long triangular prism. But if you take a squat triangular prism like this one here, then you might get a triangle. Let's see, it just broke that time. Then you might, not necessarily. Here, I have a very short line. Oh, turned into a triangle. There it is. So the triangle is what you get on the squat triangular prism. Actually, on this one, it could be a line, which is stable, but just barely so, or the triangle. There's an overlap when you have the 2 solutions. At the extremes, one solution wins out and the other becomes unstable. So it looks like Gene Taylor's theorem is right. In all the examples we looked at, the soap bubbles were meeting in 3s along curves, which met only in 4s in this very symmetric way. And she wrote a beautiful article with Fred Almgren, her thesis advisor, which appeared in Scientific American, and explained why these are the only kinds of singularities that occur even in the most complicated soap bubble clusters. And other places in nature. For example, you see in the upper right there, in that radiolarian skeleton, the bones are coming together in 4s at equal 109-degree angles for similar reasons in formation of minimizing energy, minimizing some kind of energy. Of course, more generally in the universe, there are much more general kinds of singularities, like black holes, which we talk about a lot. And I tell students when I talk that I like to think of the universe as being a big soap bubble cluster. Because, you know, if you were a little bug swimming around on that bubble there, you could swim around your whole life and think you were just on a nice sphere. You wouldn't be aware of the fact that would be discovered later on when some super intelligent bug develops a powerboat and goes sailing off to that singularity and discovers to his astonishment and stupefaction that the entire structure of his universe suddenly and dramatically changes. Well, it's the same for us. We think of the universe as going on the same forever in all directions. But someday in the future, some super intelligent human will build a spaceship, go powering out to one of these black holes, and discover to her amazement and satisfaction that the entire structure of time, space, and physics suddenly and dramatically changes. But we mathematicians know that it's good to start with simple examples And so if you want to understand the universe, start out by understanding the soap bubble. Gene Taylor's proof appeared in Annals of Math back in 1976. And I thought we'd spend the rest of the time here going over the technical details of that paper. Yeah, just kidding. Just kidding. But I'll tell you what the main idea was. The main idea is you go to a singularity, you don't know what it looks like, but you take a little sphere around it and see how the soap bubble intersects that sphere. And it intersects it in pieces of geodesics meeting in threes at 120-degree angles, as we've kind of learned. And it turns out that there are only 10 possible ways to do that on the sphere. This was finally proved by Heppisch in '64. And so you might think that means there are 10 kinds of singularities. Like number 3 there would give you the one with 4 curves over 4 lines over the tetrahedron, the cone over the tetrahedron meeting in the origin. Or the 4th one would give you where everything in the cube meets at a point. But we've seen the cube one doesn't happen, right? That's unstable. It breaks apart into 4 simpler singularities. And that's actually what happens to all the rest of them. And Gene Taylor actually did this with real soap bubbles. I saw the model she used. She dipped them in and said, no, that one doesn't happen. It breaks apart into fewer of the simpler, into several of the simpler singularities. And it turns out always into those 2 that we talked about. The others can just be ruled out as being unstable. I just saw Gene Taylor 2 years ago. We were at a soap bubble conference in Scotland. And as we were climbing up Salisbury Crag, I asked her what made her, so fortunately for us, switch from chemistry, where she started, into mathematics. And this is what Gene had to say to me.
I was a chemistry graduate student and working on my doctoral degree when I attended a course taught by Chern in differential geometry and discovered that there was a mathematics of shape and how you can talk about surfaces. And to me, this was absolutely wonderful, and I switched immediately into mathematics.
Discovered that there was a mathematics of shape. Discovered geometry and what we think of as being geometry, not like high school geometry, and immediately switched into mathematics. I said Gene and I had the same thesis advisor, Fred Almgren, although she was the one who married him. There you can see them with her stepkids there. I would go to dinner at their house. It was serious conversation sometimes. And Rob was telling me about a math paper that he was writing with his sister Anne, which just goes to prove the old adage, mathematics, it's for the whole family. But you know, I'd say that this is still quite a young field, with many basic questions still open. For example, here's one that a lot of people don't think is open. Contrary to popular belief, it's still an open question whether, if you're given a smooth wire boundary, it bounds a least area soap film. Still an open question. Now, there were lots of results that sound a lot like that. Does a least area soap film on a smooth wire boundary? Is there one? So there were some partial results in this direction. Jesse Douglas and Timur Rideau in 1936, Douglas won the first Fields Medal, proved that there's a least area disk. But if you had a disk on that twisty boundary up there, the least area disk would cross through itself in a way that we've seen that soap bubbles do not. Soap films, so that solution was not a real soap film in general. Then in geometric measure theory, it was proved that there is a nice least area oriented surface, but it doesn't allow the pieces of soap film to come together in threes the way that soap films really do. So that was in too narrow a category. The most general result was by Reifenberg, who proved something which sounded like the ultimate result. The only restriction he put on the surfaces was that some technical algebraic geometry sense, they are bounded, they span the curve. The technical thing is that the homology is non-trivial. But amazingly enough, it turns out some soap films on a wire boundary are homologically trivial, can be even deformation retracted onto the boundary, even though they're perfectly stable, real, physical soap films. So when you include the category of all soap films, it remains an open question today whether there's a least area soap film. That basic question remains open. Now, at the beginning, I talked about soap bubble clusters, which instead of having a given boundary, you're given several amounts of area that you want to enclose and separate. And they, again, still try to minimize area under those volume constraints that they're going to enclose and separate those prescribed volumes. So here's your next question, question 6. Are you keeping track? Do soap bubble clusters actually find the least area shape? How many people go with yes, always? Thank you. How many people go with no, not always? Okay, good. How many people go with C, no one knows for sure? The usual answer, correct answer today. Yeah. Well, the answer, though, in this case is no, not always. And here I'll show you 2 soap bubble clusters enclosing the same 5 areas. The only difference between the 2 of them is where the tiny 5th volume is placed. On the soap bubble cluster on the left, it's placed comfortably among larger sized bubbles. And the one on the right, it's placed a little less comfortably among smaller sized or medium sized bubbles, with the result that this cluster on the right has a little more area than the one on the left. So it exists, but it does not find the absolute minimum. It's a local minimum, but not a global minimum. And then you can ask, is this one on the left the minimizer? What do you think? Anybody see a way to do better? There's another. Where? Yes, in the back. The corner in the back is where the 3 biggest bubbles meet. So that is the most comfortable place for the little bubble to place itself. So it would be better to put it in back there. Yes, excellent, Raul. You get a bonus point. Yes, in the back there. In the back there is better. And then is that the best? Well, I think so. But it's hard to know for sure. How do you prove something like that? We don't really, in general, have methods for proving things like that. In fact, for a long time, my favorite open question was whether the standard triple bubble that you always get when you blow a bubble, and 3 bubbles come together, you always get this triple bubble shape. Maybe we'll be lucky and get it here. So here we have a double bubble. There we have the triple bubble. And there it is. It's always the same. I always see that same triple bubble combination, just like on the picture up there, if you can't see this. Is that the least area way? So for a long time, that was my favorite question. Until, finally, we realized that we didn't know if the double bubble was the least area way to enclose and separate 2 given volumes of air. Now, we mathematicians thought we knew this for a fact. And we asked this poor undergraduate, as what was supposed to be part of his undergraduate thesis, to write up the proof. But when we talked to the mathematicians around the world who knew how to prove it, turned out they didn't know how to prove it. So I asked Joel Foisey what it was like to see this, what first appeared in his undergraduate thesis as a conjecture, attract so much work and attention by mathematicians around the world. And this is what Joel said to me.
After the double bubble conjecture appeared in my thesis, and then I started hearing reports about how progress was going. It was exciting to hear that people were making progress on it, and I was happy. A small part of me was a little bit, I don't know, envious isn't the right way of word, wistful of, wanting to participate and be part of that.
So he said he was sorry he wasn't more part of all the research, but of course he was an important part right from the beginning. And he's now working with a group of his own students at SUNY Potsdam in New York State on some new open problems. But it's a great shape, that double bubble shape there. They come together, they like that. 2 separate bubbles are wasteful because when they come together, they can share a common wall. More efficient. And what else could it be? 2 separate bubbles, they come together and make this standard double bubble. Any other possibilities students here know? Yes. Excellent, yes, point for you. A bubble inside a bubble, bubble inside a bubble. There's another possibility. Of course, that's even worse because it makes the outside bubble unnecessarily big. If you moved it out, the outside bubble would get smaller. Then when you move them together, it does even better. This is why you never see a bubble inside a bubble, although I always try to get a bubble inside a bubble. These bubbles like to be outside on a warm, humid summer day. They don't like being in here today. So that's the kind of attempt I usually have. In fact, I'm afraid you're not going to believe I ever did it, but I did see it once. There's a nice bubble, getting bigger. Ha! I got my face all wet that time. Well, we aren't going to see a bubble inside a bubble. But it did happen once. Oh, there's a tiny one inside there. Look at that. Wow. Look at that bubble inside a bubble. I didn't think it was going to happen. Now, it's unstable. It's only lasted this long because there's a thin film of air separating it from the outside bubble. But if it touches the outside bubble, it immediately pops out. This is the longest I've ever had one last like that. There it goes. There it goes. Well, you're lucky today. You're lucky today. See, I didn't think I brought along the picture because I knew you wouldn't believe me otherwise. There is a bubble inside a bubble. But you don't see that much, and it's a very unstable kind of thing. Very unstable kind of thing. Next question for you guys is about this double bubble. When you have a double bubble, here's one with a little sphere on top, a big sphere on the bottom, and then there's the surface between them. That surface between them, do you think it's flat? Do you think that the big bubble pushes up into the little bubble, or that the little bubble bows down into the big bubble? So how many people go with A, flat? Minimize area, that sounds good. How many people go with B, big bubble pushes up into the little bubble? Yeah, that big, strong bubble, I'd be able to do that. How many people go with C, little bubble down into the big bubble? I think that's the majority. And the correct answer, yes, indeed. And the reason for that is there's more pressure in the smaller bubble. As you know, when you try to blow up a birthday party balloon, how you have to blow much harder at the beginning when it's small and tightly curved, and then as it gets bigger, it gets easier to keep blowing it up. Same thing, more pressure in that small bubble. Let's try a demonstration again over on the projector here. So we'll get the projector back on. I'm not supposed to make a mess here, though. Okay. So we'll take a little soapy water, maybe. That's good. A little straw here. Start with a little bubble. Big bubble. You can see the little bubble bowing into the big bubble there, right? No question about it. It's a proof. Well, maybe not. Maybe not a proof. There it is. The little bubble bows into the big bubble. Okay, good. So this is a beautiful shape. It's hard to think of any other possibilities for what a double bubble might be, well, unless you have a little more imagination. So now I'm going to show you a very strange, non-standard double bubble. This is a computer simulation by John Sullivan, who's here today. John, stand up for a second and greet the audience. You should go to his web page. John M. Sullivan, go to his webpage. There are a lot of beautiful bubble images. And there was some on the poster advertising out front. Okay, so here comes, you ready for this? This weird non-standard double bubble. There it is. There's a bubble in the center with the second bubble wrapped around it in a toroidal inner tube. Now, this is unstable and has more area than the standard double bubble. So it doesn't disprove the conjecture. But it does make you realize that there may be other possibilities that neither we nor the bubbles have thought of yet. Here's a nicer later picture where you can see how narrowly the waist of the center bubble gets squeezed by the torus bubble wrapping around it. And once you realize that could happen, why, maybe the blue bubble at the center with the red inner tube around it would have a second piece to it, a skinnier inner tube wrapping around the red inner tube, wrapping around the center blue bubble, with the blue pieces connected by a thread of zero area, if you like, or you might as well just let the blue region be disconnected. And once you realize that could happen, you could have layers on layers and layers of bubbles, maybe very lopsided, or maybe the bubbles are knotted around each other somehow. Or maybe the bubbles become fragmented into millions of pieces, maybe even with some empty space on the inside. So this is kind of the low point of the talk. It's looking kind of hopeless to prove anything. There's so many possibilities. So I'll relieve you to tell you that after about 10 years, we finally did find a proof. This was the announcement in Science magazine. One of my co-authors, Michael Hutchings, was a former undergraduate research student, and the other two were collaborators from the World Center for Studying These Problems, Ritoré and Ross from the University of Granada in Spain, showing that the standard double bubble beats all of these crazy alternatives. And I just want to show you one little lemma in the proof where everything got started, which is, of course, a symmetry argument, which is at the beginning of many geometric proofs. And it's the main proposition that is that the minimizer, the area minimizing double bubble, which we're trying to prove is the standard one, at least has to be a surface of revolution. And the lemma for proving that is that some vertical plane splits both volumes in half. Now, of course, it's easy to split one volume in half, right? If the double bubble's over here, I just start with a vertical plane, and I just march until I've split one volume in half. But now, the other volume probably isn't split in half. Maybe the big part of the other volume is in front of me. Well, I could try again from another angle. Walk until I split the first volume in half on top. Oh, no, I wasn't lucky. I didn't split the second volume in half again. I can keep trying at all different angles until I've come around 180 degrees, and now I walk until I split the first volume in half. But since I've changed 180 degrees, when the big part of the second one was in front of me before, it's now behind me. So by the intermediate value theorem, there has to be some starting angle where you accidentally split the second volume in half as well. It's like the proof of the ham sandwich theorem. So there's that way we got a vertical plane that split both volumes in half. Okay, now turn that whole picture on its side, make that plane horizontal, and repeat the argument, and you'll get a second plane perpendicular to the first that splits both volumes in half. So now we have two perpendicular planes that split both volumes in half. We might as well assume that they're the xz and the yz axes, planes, which meet along the z-axis, and that turns out to be the axis of rotational symmetry. So I haven't given you all the details, but there's the flavor of the kind of symmetry argument that's so important. And I'll give you one other little glimpse into the proof, how you eliminate this possibility of a central bubble with an inner tube in yellow wrapped around it from top to bottom. That one case. You prove that that's unstable in the following way. You rotate the left half to the left and the right half to the right. Now it gets fatter at the top and skinnier at the bottom, but by symmetry, both volumes are preserved. So you're preserving the volumes, but you develop little kinks at the dividing points at the top and bottom, and those kinks can be smoothed to second order to reduce area. Now it's much trickier when you have many layers, but that's the main instability argument in the proof. And so once that's all proved, we have a very satisfactory answer to the question, why are double bubbles the shapes they are? Theorem that minimizes energy or surface area. Now I want to appreciate that just for a minute before I tell you I'm not satisfied with that at all, really. What we'd like to prove is that that's the only stable double bubble, the only one that you'll see, because it's the only one anyone's ever seen. It's the one we see all the time. And I love this conjecture because we mathematicians have no idea how to approach it. And yet, a kindergarten student could solve it next week by just blowing a different double bubble. That could happen. That would be a great resolution. A remarkable thing that happened was on the heels of our proving this theorem, a group of students over the summer generalized the result to hyperbubbles in four-dimensional space, proving that there still the standard double bubble with two spheres coming together is best. Although instead of the 6 difficult cases we had to deal with, they had, as I remember, over 100 difficult cases. So I asked Ben Reichert, who was the leader of that group, if there was anything that he wanted to say. And here's what Ben had to say for you.
I wrote down all the possible alternative minimizers in R4, about 200 of them.
200.
Eliminated them individually or in small groups to leave just 2 or 3 unresolved problem cases. But instead of finishing the proof off, the next week I got more ambitious and tried to classify general cases in higher dimensions.
Higher dimensions.
I eventually found a single case in R5 which could not be eliminated by our method.
Got stuck in R5. And this is what the picture looked like in R5 before you rotate it. That's the general, before you rotate it around the axis. And in this case, the bubbles are so lopsided, that can happen in higher dimensions, that all the arguments broke down. So it sat like that for about 5 years, until in 2005, Marilyn Daly, another student, eliminated that particular case, thought she could solve them all, finally sent her general argument to Reichert. He pointed out an error and suggested a new route of inquiry. But then I got a message from her. She said, "Goodbye, I just bought a one-way ticket to China and may never see you again." So that was the end of that effort. But Ben kept working at it, and 3 years later proved the result in all dimensions. So it's now known in all dimensional spaces. The double bubble. But now I want to go back for a minute to the single bubble in some higher dimensional or curvy universes other than Euclidean space. So I already talked about how in the plane back in 200 BC, Zenodorus proved the circle best. Three-dimensional space, Schwarz in 1884. Higher dimensions was done by Lusternik in 1935. Symmetry arguments are the way to go. Similarly, on the sphere, like on the surface of the Earth, a round disk is the best way to enclose a given area. And that holds in all dimensions, higher dimensions too. Also in higher dimensional hyperbolic space, it's just a round ball. These were proved by Schmidt in 1940. But if you double dimensions by moving from real variables to complex variables, the analog of the sphere is then complex projective space. CP1 is a two-dimensional thing. In fact, it coincides with the two-dimensional sphere. So we know there that a geodesic ball is the solution. CP2 is a four-dimensional analog of the four-dimensional sphere, still very symmetric. And there, it's still conjectured that the geodesic ball is the best soap bubble, but an open question today, even in this very symmetric space. But you don't have to go to strange spaces. Suppose you just take a region in the plane or a region in space, and you want to, let's say, a volume 1, and you want to fence off some fraction of that region. Well, the best way to do it usually is fencing off some corner, as we did in the shape on the right. For that reason, it's very inconvenient to be located in the ball, because there's no corner to fence off. The conjecture is that it's more expensive to fence off some fraction, given fraction of the volume in the ball, than in any other convex region. That the ball is the worst place for fencing off some fraction of the unit volume. This is also open, this conjecture. The only case that's proved is in the plane when the fraction that you want to fence off is half. And that was a fairly recent result, just in 2012. So there's an amazing problem still open. Take the particular example of the nicest shape, one of the nicest convex bodies we know, the cube. Here again, there's a wonderful conjecture about what's the best way of fencing off some fraction of the cube. If it's a little volume, just put it in a corner with a spherical cap. If it's a larger volume, put it along an edge enclosed by a cylinder. And if it's a still larger volume, going up to half the volume of the cube, just take a plane fencing off a slab. And then for more than half, it just goes backwards, the complement of the slab, the complement of the cylinder, the complement of the corner. So that's the conjecture. Still open. And here there's some good alternative candidates. Constant means curvature surfaces due to Lawson and Schwarz, which actually do very well. This Lawson surface comes within 0.03% of beating the cylinder. Maybe that's why this is so hard to prove. And actually, Roman noticed that if you just skew the cube a bit, then the Lawson surface beats the cylinder by 0.02%. So it's a very delicate problem which remains open today. Here's an even more technical one, the so-called Subramanian-Heisenberg group, a very interesting and popular space with mathematicians. Ponsou back in '82 conjectured that the ideal soap bubble is a union of surface of revolution made up of spiraling geodesics. It's a very intriguing space. Just in January 29th it was, a solution was posted on the archive, withdrawn 3 weeks later. So this is still a very stubborn, active area of research. There's been a lot of work for the past several years talking about trying to understand the universe, and the key ingredient is what large soap bubbles would look like. The conjecture is that in many cases, large soap bubbles will be nearly round, even if the universe has a black hole and other distortions. And that's been proved in certain cases with certain qualifications. The latest result was just posted March 17th, so not very long ago, by Chodish and Eichmar and Volkmann, about universes that are asymptotically conical as you go off to infinity. So this remains a very active area of research today. But back to our contest, ladies and gentlemen. Question 8. We talked about the double bubble in space, enclosing and separating two volumes. What about the easier double bubble conjecture in the plane, where the best way to enclose and separate two areas is just 3 circular arcs meeting at 120 degrees? History question, when do you think that was proved? Ancient Greeks? Middle Ages? Time of Euler and the theory of calculus? Recently. So how many people go with ancient Greeks? Yeah, why not? How many people go with Middle Ages? Got someone there. You know, the good thing in voting in the minority is if you win big. You're getting a point no one else is getting. How many people go with C, time of Euler and the theory of calculus? Okay, we've got some more people there. How many people go with D? Recently? Correct? That's right. In fact, it was proved by a group of students working over the summer, led by Joel Foisey, whom you met early on. He spoke to you about that work. They proved the theorem, published it in the Pacific Journal of Math. In the introduction, mentioned some open problems like the double bubble in space, which I've told you was solved, published in 2002, and the triple bubble in the plane, which had hundreds of cases, and so was solved by one of John Sullivan's graduate students, Wachar and Wichi Ramallah, even later, in 2004. So here's the whole situation in the plane, what's known. Best single bubble, yes, that was ancient Greeks, Zenodorus. Best double bubble, this group of students did the work in 1990. Best triple bubble, Wichi Ramallah, 2002. Best quadruple bubble for equal areas in the plane, open today. We think this is the answer. No one's been able to prove it. I visited Wichiramala in Thailand, where he has some bubbles with his daughter there, and asked him why he hadn't done that yet, and he had a short answer. Too hard. Too hard. All right, ladies and gentlemen, this is the moment of truth. Of those 8 questions, how many of you got at least one right? Excellent. 2 or more. 3 or more. 4 or more. 4 or more questions right? No, very few people. Okay, those with 3 or more are finalists. You can come down front now. You have 10 seconds to get down here. 3 or more answers right. Come down front. You are our finalists. You have 10 seconds. 9, 8. If you don't come, we'll see what we'll do. Oh, good. There they come. There they come. We're going to have a couple of finalists here. And they're going to have to guess, as my students did, which, for example, is the best 5-bubble cluster. Which is the best 5-bubble cluster. So we want to minimize the total perimeter, outside and inside. If you think it's the one on the left, go to the left. If you think it's the one on the right, go to the right. Left or right? You have 5 seconds left. 4, 3, 2. Okay, they all like the one on the left. Audience, what do you think? You like the one on the left? How many people like the one on the right? Evenly divided. Well, they did experiments on a Xerox machine, measured it pretty carefully. And the better one is the one on the left. Congratulations, gentlemen. Off to a good start here. It's going to get harder when we go to 6 now. Left or right? All staying on the left. What do you think, audience? How many go with the one on the left? How many go with the one on the right? The audience thinks the one on the right. Nobody wants to change? It's very close. It's very, very close. The students couldn't tell. It was within their margin of error. The one on the left seemed slightly better, but we had to wait 3 years for some computer experiments by some European scientists who proved that actually it's the one on the right. But I guess you can stay up here because nobody got it right. Okay, now get serious here. 7. Now that's too easy. It's the one on the left. Now we go to 8. When I go to 8, there will be 4 choices. Right? You are not allowed to pick the same choice. The first one to answer can pick any one. The second one to answer can pick one of the remaining 3, and so on. When you have your answer, just say upper left, lower right. Lower left, upper right. Okay, you ready? Okay, here we go. Upper right, stand right over there. Go to the right. Upper right. Upper left, you can stand right there. Lower right with the hole in the bottom. Okay. Lower right. Okay, you're right over there. You can stand right there. That's good. Stand right there with that. Let's see. What's the answer? The answer is upper left. Yes. So we have a champion. You stand right there. Don't go anywhere. You guys were great. Thank you. You just need to do a little more research. And I have a startup kit for you here. So there you go. Congratulations. Congratulations. All right. Good work. Congratulations. And now we've got our champion here. So your name is Nikolai Hansen, and your status here?
I'm a PhD student here.
A PhD student?
Yeah.
Where exactly?
Mathematics department.
Right here at this university in the mathematics department. All right, and how did you do so well in this today?
I guessed.
He guessed. And you see, that is the secret of all of this, guessing. So of course you get, because when you guess, sometimes you're lucky and you get the right answer, but even if you got the wrong answer, I have a better prize for you, Nikolai, my math chat book here, and I'm going to inscribe it to you. So this is to Nikolai, soap bubble geometry champion.
Thank you.
Congratulations.
Thank you very much.
So do you think you could do this now, folks? Oh. Well, I gave him credit there, you know. Although actually, because I wanted a winner, and it's the best of the three, although actually, the one in the lower left turns out to be slightly better. Although no one picked it. But you were the winner today. That was fair. Just to check, though, do you know which of these 10 clusters would be best? Middle left? Like that? The students like bottom left. Upper right? Middle right. Or 11? Students like lower left? They were right. Last one. Students like lower left? Upper left. So it's really hard to tell. It's hard to find a pattern, even for this very simple problem. These were some of the examples sent by the European scientists, and it's fun to look at them and try to guess what's going on, but we really can't tell yet. So there are lots of wonderful open problems at all levels here, and your homework is to go out and tell the world, because you're the ones to do it, how much fun, how interesting mathematics can be. And my final document shows that it's never too late or too early to start enjoying mathematics. Here I am getting my first soap bubble geometry lesson from a rather special teacher, my mom. So, thank you very much.